Hello, my name is Daniel J. Denis. I am in the Department of Psychology at the University of Montana. And in this brief presentation, we want to talk about the 95% vaccine efficacy computed on the Pfizer data. We'll talk about how that 95% figure is computed, and then we'll talk about a few teaching opportunities afforded by looking at data such as this to highlight some statistical and research issues. And then we'll close out with a brief quiz to evaluate knowledge. So the first thing to look at here is this particular table, which is vaccine efficacy against COVID-19 at least 7 days after the second dose. So this was a 2-dose vaccine. This was an experimental study. This was the group receiving the vaccine. So there's your treatment group, and this was the placebo group. Now the placebo group received something like a sugar pill or a fake pill. So you can call that the control group over here. Now, the outcome here was the COVID-19 occurrence. Did the person develop COVID-19 or did they not? There are N's per group. There's the N in the vaccine group and the placebo group at the given efficacy endpoint. Now, when they actually computed the 95% vaccine efficacy, they used these numbers over here. And those numbers are per 1,000 person years. So they're a little bit different than these bolded numbers. But whether you use one set of numbers or the other, you are going to get 95%. The difference will be in the trailing decimal points. For our purposes, we will use these numbers since those are the numbers used by Pfizer. One point before we start is it may be tempting to look at this 8 versus 162 directly. Now, these are the number of people in the vaccinated group that developed COVID-19. This is the number in the placebo group that developed COVID-19. But we can't simply compare 8 to 162 directly because they're based on different amounts of information. So what we need is the computation of a rate. So I'm going to go to this 2x2 table and put another heading here. And this heading represents COVID-19 yes. These are individuals developing the virus, and COVID-19 no. Here we have the vaccinated group. Here we have the unvaccinated group, which is referring here to our control group. From there, we can look at what these cells represent. The A represents those in the vaccinated group developing COVID-19. So that number is right up here. So it's the 8. We can put the 8 right down here. This B represents the number in the unvaccinated group developing COVID-19. So that number is 162. From there, we can report these numbers as well because A plus C has to be the sum of these two cells, and that's going to be the 17,411 right here. And the unvaccinated will be the 17,511 for the B plus D. Now that we have those numbers in the table, we're all set to compute what are known as attack rates for each group. So this particular table is the same thing as this table up here. It's just cleaned up a little bit so we can define those attack rates. The attack rate for the vaccinated is equal to A divided by A plus C. Well, that's A divided by A plus C. And that agrees with the numbers we have up here, 8 over 17,411. The attack rate for the unvaccinated is computed as B over B plus D. So that's B over B plus D. And that's exactly what we had up here when we wanted to take this number and divide it by this number. So there are attack rates for both groups. When computed on our data, here they are. 8 over 17,411. 8 over 17,411. There it is, cleaned up a little bit. The attack rate for the unvaccinated is 162 over 17,511. That's 162 over 17,511, or B over B plus D. So we have two attack rates, one for the vaccinated group and one for the unvaccinated group. Now, when you look at this, it becomes clear that the preference would be that the attack rate for the vaccinated group is less than the attack rate for the unvaccinated group, because that would suggest that the vaccine is having some effect. If the attack rate for the vaccinated group were equal to the attack rate for the unvaccinated group, that would suggest that the vaccine is not having an effect. So right away, even by looking at those two attack rates, we can appreciate a little bit what we're looking for when we look at the formula for efficacy. So let's see how efficacy is defined. The first thing to note here is this formula says effectiveness. And there's a little bit of a difference between efficacy and effectiveness. The efficacy is a term often used to describe what happens in the controlled lab experiment. So what Pfizer did was an experimental design with rigorous controls. Therefore, that 95% would be referred to as efficacy. The effectiveness is often referred to when giving the vaccine to an uncontrolled population or group. So when they give that vaccine out to the population, they're interested in studying how well it works in the population, and that would generally be referred to as effectiveness. Sometimes the two terms are used interchangeably, but they have that slight distinction. For our purposes here, whether we compute efficacy or effectiveness, we're going to get the same computation. So let's compute this right here. Attack rate for the unvaccinated minus the attack rate for the vaccinated. That's what's appearing in our numerator of our formula. In the denominator, we have attack rate for the unvaccinated. Now, the best way to understand this formula is to kind of drive it to its extremes. What would be the best case scenario for the vaccine? Well, the best case scenario would be that we get an attack rate of 0 for the vaccinated group. What would that mean? Well, going back to our original data, that would mean that this number, instead of equaling 8, would equal 0. That would mean that those in the vaccinated group, 0 people develop COVID-19. It would be the absolute best case scenario for that vaccine. Well, under that situation, what happens to our formula? We take attack rate unvaccinated minus 0 divided by the attack rate for unvaccinated. So that number will equal 1. It equals 1 because we're dividing the same number by itself over here. When we multiply by 100, we get 100% efficacy. And again, that agrees with our intuition because that means that, in this case, 0 people are getting COVID-19 in that vaccinated group. Now, we can also drive the formula to its other extreme. Imagine that these two are equal for a minute. Attack rate unvaccinated is equal to attack rate for vaccinated. If that were the case, then the numerator is equal to 0. That whole numerator would equal to 0 because these two rates would be the same. Well, if the two rates are the same, that would suggest that the vaccine is not having an effect, which is exactly what the formula would be reporting, because you'd have 0 divided by the attack rate for the unvaccinated would equal 0. So again, just kind of driving the formula to its extremes, we can appreciate what it's actually measuring. And now we can use the Pfizer data, input those numbers, and see what we get. So here it is, vaccine efficacy, 162 over 17,511. That is the attack rate for the unvaccinated, right over here, minus the attack rate for the vaccinated, 8 over 17,411. So there's the attack rate for the vaccinated. That's the number we're putting in. And that divided by the attack rate for the unvaccinated. When we compute that, we get 0.95. Make sure to multiply it by 100 to get the percentage. And there is the 95% efficacy computed by Pfizer. As promised, we want to talk about a few teaching opportunities afforded by looking at data such as this. And the first one is that of experimental design. So this was an experimental design, and it had to be an experimental design to try to figure out whether that vaccine is effective. So when they took participants, they had to randomly assign to the vaccine group or the control group. It was really important that they didn't decide, for instance, to put all young people in the vaccine group and all old people in the control group. There had to be an element of random assignment, and there had to be strong controls put into place. For instance, it would be incorrect to simply study this group. If you do not have the comparison group, you cannot make that contrast and try to figure out whether that vaccine is working. So experimental design here is an absolute must, which is one reason why Dr. Birx and Dr. Fauci have been saying for many months that until they see the gold standard of the experiment, they simply will not know whether a vaccine is effective. You absolutely need the experiment here. Another idea is the idea of within group variability in experience. And what we mean by that is when you look at this particular group, it becomes very interesting why 8 people who receive the vaccine develop COVID-19. And that is information that's happening within the group. The 95% efficacy, we're doing a comparison between the placebo and the vaccine group, but even looking within the group can reveal a lot of rich research questions. For instance, why did they get it? Why did the people who received the vaccine, 8 people, also develop COVID-19? Was there some kind of commonality of those people? Did they all have weakened immune systems? Did they receive a little bit more of a viral load? Or was it separate instances and separate contributors in each case? Either way, we can bet that researchers are studying things like that as follow-ups to this particular research to try to better understand COVID-19 and also understand where that vaccine is most effective. Because if there is a commonality of those 8 people and they had, maybe weak immune systems or something like that, then that would be very, very useful for researchers to know so they can plan more studies. And again, the professionals in the area will have some really good hypotheses as to why potentially those people were not protected. The other idea here is that of statistical and inductive inference. Now, this vaccine research was conducted on a sample of data, and they computed the 95% on the sample. However, what we are most interested in is what is going on in the population. So that process of generalizing from sample information to population information is what scientific induction is all about. And this is where statistical inference becomes very, very useful, because we ask the question, if what is true of the sample, to what extent is that true in the population? And this idea here is that will the 95% figure hold in the population? There's always a little bit of gamble when you generalize from the particulars to that wider set of observations. 95% may increase, it may decrease. They just don't know until they give that vaccine to the population. It also highlights the idea that they may learn more about where that vaccine is effective. For instance, perhaps this person develops an allergic reaction to the vaccine. That person was not in the sample. So that gives an instance of learning more of who may not be protected by the vaccine. And that's what scientific inference is all about. A little bit of risk involved. Now we're hopeful that the 95% holds in the population, but the point is that we don't know until you actually test it on the population. The other element here is the idea of a decision and risk analysis, and that's simply to say that the decision of whether to get vaccinated or not, so a yes/no decision, has many contributors to it. So the 95% efficacy is definitely one contributor, one influence to that decision, but there may be more. And the point here is to say that statistics or numbers should never make decisions for us. And sometimes a little bit of the disdain for statistics that sometimes arises because people do not want statistics making decisions for them. But they're not designed to make decisions for us. They're simply designed to inform decisions. And the whole context of the decision-making process should be taken into account. For instance, if it's found that there's a shortage of vaccines, then even though it's 95% efficacy, you also have to incorporate the idea that there's a shortage. So maybe the vaccine should be prioritized to the elderly or the sick, and that would also influence the decision of if and when to get vaccinated. Okay, let's do a quick test of knowledge. I'm going to read the question and then allow about 5 seconds for you to think about the answer. Then I will give the answer and then we will recap it. So number 1, an experimental design is not needed to determine the effectiveness of the COVID-19 vaccine. True or false? Okay, so that one would be false. As mentioned, we definitely need the experimental design to determine the efficacy of the COVID-19 vaccine. Now, one little caveat here is this word is effectiveness. So if you picked up on that and you noted that there is a distinction between effectiveness versus efficacy, then you could have also answered true and also gotten the point there. So that's one of our favorite types of questions where whether you answered false or true, you can get the point either way. Number 2, the 95% efficacy computed on the sample is guaranteed to hold when the vaccine is administered to the population. True or false? Okay, so that one would be false as well. As mentioned, the 95% efficacy is computed on the sample, but by the process of scientific induction and inference, they do not know yet how the vaccine is going to perform on the population. Again, if you like to make the distinction between efficacy and effectiveness, remember that the 95% is on that controlled lab experiment, and now they're going to learn of the effectiveness of the vaccine as it's given out into the population. Again, that's why the experimental design is needed to determine the efficacy, but when it's administered to the population, you don't need the experimental design because you're now in the realm of determining the effectiveness of the vaccine. Number 3, a useful follow-up investigation would be to study why 8 people who received the vaccine still developed COVID-19. Okay, true or false? Well, that would definitely be true. As mentioned, that becomes a very, very rich research question as to why those 8 people who received the vaccine still develop COVID-19. And as mentioned, if there are characteristics of those people that the experts in the area would study, maybe tell us more about where that vaccine is most effective and perhaps who is not protected by the vaccine. So that could help us because, maybe you get vaccinated, but if you're the same type of person that was not protected in the experiment, well, then maybe you still have to be careful and socially distance and take precautions. So that could be a very important thing for informing us on the efficacy and effectiveness of that vaccine. Okay, I want to thank a couple students who did a few computations with me and talked with me about the paper. That's Gabriella G. and Amber Thatcher, both in the Department of Psychology at the University of Montana. They were very helpful. And last but not least, we know that before things like vaccines make it into our arms, they make it into the arms of our other animal friends. So I just want to give a shout out to the animals who have helped develop this vaccine. They don't get the credit they deserve. And as a tribute, if you are considering getting a cat or a dog, we definitely do not need more breeders, but we do need more adopters. So please feel free to visit your Humane Society of Western Montana. There's a loving cat, there's a loving dog just waiting to be adopted. They're here for us. Let's be there for them. Thank you. I hope you've enjoyed the presentation. Have a great day.